Hello, this is Math Jazz from Almost Cool, and today we're going to be talking about cardinality in our live stream. So, let's cardinality is a way of measuring the size of a set. We did this at the beginning of the semester just by counting the elements. That's what cardinality is for a finite set. However, infinite sets are, it's hard to count how many things are in an infinite set. But there are different sizes of infinite sets, so it's not useful to just say that they're infinite. Usually, well, a lot of times it's good enough to just know that they're infinite or not. But some infinities are bigger than others, and so we're going to generalize our cardinality from being able to just count elements to a more general and more useful definition. It will allow us to tell the differences between things that are infinite like the natural numbers, 1, 2, 3, and so on, or infinite like the real numbers, like the number line. There are more points on the number line than there are natural numbers. And so we'll get to this. It's this section in our book. The quote at the beginning says, "It's very much like you're trying to reach infinity. You know it's there, you just don't know where, but just because you can never reach it doesn't mean that it's not worth looking for." That's a neat quote. The authors have picked some really neat books to quote in this. They've picked some really neat books to quote in this book that they've written. So. And this intro is basically what I was saying about how we're going to talk about more useful ways of measuring the size of sets. So, I guess the first thing is our definition here. So let S and T be sets. We say that they have the same cardinality if there's a bijection between the two, and we use this notation to represent that. So, I mean, we've actually used this notation in previous sections. In fact, I think section 27, we proved some things about cardinality, even though we hadn't rigorously defined cardinality yet. So, anyway, if they have different cardinalities, we will write this notation. Okay. Theorem. The cardinalities of n and z are the same. Well, let us prove this. I mean, the proof is in the book, but we might as well get used to figuring out proofs on our own. So, the definition of having the same cardinality is, so cardinality of S equals the cardinality of T if there exists a bijection from S to T. Now, it's the same as having a bijection from T to S. Bijections can be inverted, so it doesn't matter which direction you go on that. But we only have to find one in one direction because we automatically get one in the other direction for free. And by that, I mean having a bijection from S to T. If we have that, we invert it to get the one from T to S. That's how. So if S has the same cardinality as T, then T has the same cardinality as S, because we can just reverse the bijection. It gives us a new bijection going the other direction, and works like that. Okay, so this is what we're trying to prove. And we're trying to prove that the natural numbers and the integers have the same cardinality. So this is actually something that we proved without knowing it in 27. In section 27, there was a function that we defined that went from, it was f goes from z to the Cartesian product of 0, 1, and n. And it went like this, that f of x equals 2x No, it went like this. Went to 0, comma x if x were greater than 0, and we went to 1, comma 1 minus x if x were less than or equal to 0, or something like that. So anything like that would have worked for the proof of the problem in the last section. So, and I'm saying that this is the same proof because we can cook up something very similar to this to get n and z being the same cardinality. It'll go like so. So we'll have f of x. We want f to go from, do we want it to go from z to n or n to z? We can do it either direction. Let's do from n to z. We'll make a bijection. Here's n going to z, and we'll do it like this. We'll have n over 2 if n is even, and we'll go to, let's see, 1 minus n over 2 if n is odd. I claim this is a bijection from n to z. If that's true, then we have our proof of the two sets having the same cardinality. So let us prove this. Injective. So if f of x equals f of y, then, well, that means, so these numbers are positive because I'm taking a positive number over a positive number. These numbers are not positive because I'm taking 1, 3, 5. So I get 1 minus 1 is 0 over 2 is 0. That's not positive. Or 1 minus 3 is negative over positive is still negative. I either get 0 or I get a negative number on the top. So that means that this fraction will be negative. So either they're both positive. So f of x equals x over 2, which equals f of y, which is equal to y over 2. And hey, look, if f of x equals f of y, then x equals y. On the other hand, if both are negative, so that means that f of x equals f of y means that we have 1 minus x over 2 equals 1 minus y over 2, which means that 1 minus x equals 1 minus y, which means that x equals y. And look, that's injective. Well, now we have to prove that f is surjective. Let's get some more paper. So, f of x equals, let's copy it down. We have x over 2 if x is even. And we have 1 minus x over 2 if x is odd. So, let y exist in z. If y is positive, then let x equal to y. Then f of x equals x over 2 equals 2y over 2, which equals y. So we hit all of our positive integers. Let y let y be less than or equal to 0. Then let x equal, let's see, negative 2y plus 1. Is that what we need? We'll tweak that if we need to get it right. F of x equals 1 minus x over 2, which equals 1 minus negative 2y minus 1 over 2. The 1's cancel. We get 2y over 2. The 2's cancel, and we're left with y. So this is surjective. And F being surjective and injective means F is bijective. And that means that the natural numbers have the same cardinalities as the integers. Okay, so we were able to prove that ourselves. Well, let's take a look back at the book and see if our proof matched up with the book. This is how you should study for math classes, by the way. Look at the statements that are made and see if you can construct them yourselves. So it says here we need to construct a bijection. That's what we did. Count the elements. The first idea is to count 0, then successfully. Okay, so it says take 1 and map it to 0, 2 and map it to 1, 3 and map it to negative 1, and so on. And this is obviously a bijection. We actually did one better than the book's proof, because we actually gave the proof that our function was a bijection, and we gave an equation for it. If you notice, looking at our equation here, if we plug in some values for f, let's do that in another color over here. Is that a good color? Yeah, that looks like a fine color. So if we plug in the values 0, 1, 2, sorry, not 0. 0 is not a natural number. If we plug in the numbers 1, 2, 3, 4, 5, ... into our function, what do we get out? Well, plug 1 in. 1 is odd. 1 minus 1 is 0. Over 2 is 0. So we get out 0. Plug in 2. 2 over 2 is 1. Plug in 3. 1 minus 3 is negative 2. Over 2 is negative 1. Plug in 4. 4 over 2 is 2. Plug in 5. 1 minus 5 is negative 4. Over 2 is negative 2. And if you're noticing a pattern, that's because there is one. 0, 1, negative 1, 2, negative 2. And if we look back at the book has precisely the same pattern. We gave the same function as them, although we built it up ourselves. And we built it up using an equation. We gave an equational definition of our function instead of just listing the elements. And then we proved it was a bijection rather than just stating it's a bijection. Okay, so let's see. Oh, remark. The previous proof was very informal. First, we didn't prove the function is injective and surjective. Well, and here's the equation, the one that we came up with ourselves. Okay, so, ooh, and there's this. That's kind of a neat looking way to write it. Okay, so we have our first example of proving two sets are bijective. Let's continue. Theorem says the relation of having the same cardinality is an equivalence relation. Okay, so let's prove that. Oops. Um. Oh, yuck. There we go. Okay, so let us prove our proof. Our proof is going to be, we want to know, what is the proof? Oh, we want to prove that cardinality is an equivalence relation. So, if we recall, to be an equivalence relation, we need three properties. The first one is reflexivity. The next one is symmetry. And the last one is transitivity. So, we're going to prove that our cardinality relation that we've discussed has these three properties. Let's start with reflexivity. So, reflexivity. Is every set the same cardinality as itself? So, yes. Let's prove that. Like, let A be a set. Let F go from A to A by f of A equals A for all A in A. And this seems like a really dumb little function to construct. This function is called the identity. It sends every object to itself. Now, is this a bijection? Well, let's see. So, here's our injective. So, if f of x equals f of y, then, well, what's f of x? F of x equals x. And what's y? Well, f of y is equal to y, so what do we get? X equals y. And that's the definition of injective, is that if f of x equals f of y, then x equals y. So we have injective. Now surjective. So if y exists in A, which is the codomain of our function, let x equal y. Then f of x equals, well, it equals x, but x equals y. Hey, look, we found an x such that f of x equals y. So surjective. This was the injective part. Okay, so if we're injective and surjective, we're bijective. If we have a bijection from A to A, then A has the same cardinality as A. So, yes. So that means that same cardinality as is a reflexive relation. The next thing we need is symmetry. So we're going to go, suppose, go. Here's 2. We're going to prove it. Suppose A has the same cardinality as B, or we'll write this from now on. Well, we want to show that B has the same cardinality as A. All we know is that A has the same cardinality as B, so that means that there is a That means that there's a bijection from A to B we get that because we're assuming that A is the same cardinality as B. Well, F inverse is also a bijection. And F inverse goes from B to A. Well, if we have a bijection from B to A, we get that cardinality of B is equal to A, or the cardinality of A. So that proves symmetry. That was actually easier than reflexivity, which is usually not the case. Usually when you're proving something's an equivalence relation, reflexivity is the easy part. So now we need to prove transitivity. So 3. Suppose that A has the same cardinality as B, and B has the same cardinality as C. Well, then what? Well, there exists bijections. Bijections. F from A to B, and G from B to C. Well, we don't even need another name. We're not going to name this. We're just going to go G composed with F goes from A to C. That's going to be, you take F and plug it into G. That'll get you from A to C. Is a bijection. Because the composition of bijections is a bijection. So we have a bijection from A to C, so A has the same cardinality as C. That's it. We just proved that that cardinality is an equivalence relation. So let us go back to our book and take a look at what our proof is. See how we did. We proved this relation is reflexive. The identity function is the bijection. Done. Proof symmetric. We take the inverse function of our bijection. We get another bijection, and we're done. And transitivity. We take the composite function. We get a bijection, and we're done. That's it. Now, they did not prove that the identity was a bijection. I'm assuming that that's probably in the section of the book on surjectivity and bijectivity and injectivity. So they probably proved that earlier. We proved it ourselves here, and that's okay. Okay, so definition of countable sets. That's countable if it has the same cardinality as the natural numbers. That's a useful thing. It's a pretty simple definition, so we'll just keep going. But it's a useful thing. Let's see. To show that a set is countably infinite, you need to arrange its elements in a non-repeating infinite list. Well, yeah, because a list is just a bijection between some subset of the naturals and the object that you're listing, or the objects that you're listing. See? So like right here, this is a bijection between the set 1, 2, 3. See, 1 goes to A1, 2 goes to A2, 3 goes to A3. That's our bijection there. Okay. This is what we did when we proved Z is countably infinite. Yes, we made a list, and it was in that order. 0, 1, -1, 2, -2, 3, -3, and so on. Yeah, and if you skip elements, you're not surjective, so you don't have a bijection. And if you repeat elements, then you're not injective, and that's not a bijection. Okay. Which of the following lists proves that Z is countably infinite? So B repeats 0, so it's a bad list. 1, 0, 2, -1. Oh, 1, 2, 3, 4, and 0, -1, -2, -3. Yeah, this one proves it. Why doesn't this one prove it? Well, I'm gonna claim this actually does prove Z is countably infinite. Oh, okay. No, it proves that it's at least countably infinite. It might. This list here shows that Z is at least infinite because it contains the naturals. But it contains more than the naturals. And some of the elements are not appearing in this list. So from this one point alone, A, we don't know that Z has the same countability or the same cardinality as the naturals. We just know it has at least the cardinality of the naturals. But it might have a larger cardinality than the naturals. We proved in the example problem that that's not the case, that they have the same cardinality. But this list here that's highlighted doesn't show that quite. Okay, let's keep going. Any infinite subset of a countably infinite set is countably infinite. That is true. So, did we try and prove this? Well, yeah, we should. Although I kind of do want to get to the homework, but the proof goes something like this. I mean, you're probably reading it on the screen, but it's since we're dealing with. Okay, let us just do this. We'll just do it. Okay, so here's our proof. We have let A be a subset of S, such that A is infinite and S is countably infinite. We want to prove that A is countably infinite. Okay. So, first of all, what's the definition of infinite? Well, a set is infinite if there is a bijection from itself to a proper subset. Okay, so that's all we know about A. We know S is countably infinite. So there exists a bijection between S and N, because that's the definition of countably infinite. So there's a bijection between S and N. So that means that there's a restriction of this function that goes from A to N. Is the restriction the best way to go? Yeah, probably. Okay, so we have this relationship that goes from A to N, giving us for every A there's a natural number. This this relationship is, or this function is injective, because the restriction of an injective function is injective. Now we need to somehow use this tool to give us a bijection between the naturals and A. So let G go from, let's say, A to N. No, go the other way around. N to A by G of N equals the well, let's do it this way. G of 1 equals the A in A with lowest f of A. Okay, so there's got to be one of these because f of A is a natural number, and the natural numbers have something called total ordering. That means that whenever you have a set of natural numbers, you have a lowest element. Okay, so if we look at all of the objects in A, we take f of them, we have a collection of natural numbers. That means we have a lowest one. G1 is going to be the A that has the lowest. If Gn equals A and f of A equals M, let G of n plus 1 equal B such that f of B is the least element of f of capital A with f of B greater than M. So basically what we're going to do is that the first G1 is just going to be the A that has the lowest f value. And then for every one we've defined, we'll define the next one by taking the next lowest f value. That's probably a shorter way of writing it. Let's try writing it that way. Okay. Okay, so for every n greater than or equal to 1, define G of n plus 1 as the A with lowest f of A greater than G of n. There we go. So whatever value, so for n, sorry, that's not quite right yet. F of G of n. There we go. So for every natural number, we define, so for 1, we've defined G of 1 to be the A with the lowest f value. And then for every natural number after that, we define G of n plus 1 as the A with the lowest f value greater than the one that we previously defined. A in A. There you go. Now, this function here is going to be surjective because there are an infinite number of A's. So we can't reach an end, we'll hit every natural number, because if we missed a natural number, that means that we only had finitely many of the a's to choose from. And we can only hit each natural number once, because if two a's went to the same natural number, that would break this part of the definition, that each element we define is going to be the next element of a with an f value that is strictly greater. So that's the verbal proof that will prove it's a bijection, but here we go. Bijection. First part is to prove injectivity. So here's our injective proof. Suppose g of n equals g of m, then, well, what does that mean? Well, that means that f of g of n equals f of g of m, and f is injective because it's this restriction of a bijection. So so they have the same output value, which means they came from the same. No, that doesn't quite prove that. Suppose g of n equals g of m. So we're grabbing the same a value. Same a and a. Okay. So, well, that has to, because if they didn't, if n and m were different, then let's say m was the smaller one. If m were the smaller one, then that means that g of n picks out an element of a, and that has some f value. And then g of m, since m is defined later, g of m's f value has to be strictly greater than g of n, because we picked each of these f values to be strictly greater. But if they have different f values, then they can't be the same element of a, because f of a is a function from a to n. So we can't have f of a being two different values. So let's write that out. So this is a proof by contradiction, which means we should probably start it here. Suppose this, and m is not n. By symmetry, we'll pick n is less than m, because that's always going to happen. If you have two numbers that aren't equal, one's going to be smaller, we'll just name the smaller one n. Then g of n equals a, and f of a is some natural number. And then we go, well, g of m equals a, and f of a still equals the same natural number. But we know that f of g of n plus 1 is strictly greater than f of g of n for all n in the naturals. So f of g of m must be strictly greater than f of g of n. And that's a contradiction. So g of n equal g of m implies that m equals n. Okay, so the other part, surjectivity. So suppose that A exists in A. Then f of A equals some natural number, all its n. Then g of n, well, that's going to be strictly greater than, well, it's going to be greater than or equal to n. Why? Because what we know is that, f of g is going to be greater than or equal to n, because we have best case scenario is that the A's all line up perfectly. A1, no, 1 goes to A1, 2 goes to A2. So this is our G, and here's our F. So we go from the natural number 1, and we have G of 1 equals A1, and F of A1 equals 1. And we have G of 2 equals A2 equals 2, and so on. So n goes to A sub n goes to n. But what we know is that with f here, f sometimes skips a number. Like, so we could have 1 to 1, 2 to 2, 3, or we could have 1 to A1 to 5, 2 to A2 to 10, and so on. Because we know that the way that we're building G is that each of these goes to the A with the smallest, and so closest packing gives us 1 A1 1, 2 A2 2, 3 A2 or 3 A3 3, so on. But that might not happen. We might have A's that are quite spaced out, so we might go 1 A1 10, 2 A2 100, 3 A3 1000, and so on. But what happens is that this number cannot be smaller than that number, because you can't go from your counting numbers, skipping counting numbers, and end up smaller than if you're going monotonically. So, so that means that suppose that A exists in the set A, then f of A equals some natural number n, then f composed with g of n is greater than or equal to n. So for some m less than or equal to n, not f, g of m equals a. Well, why is that? Well, we know that f of g of n is greater than or equal to n. So that means that g of n is either a, or g of n has bigger f value than a. The first case means, hey, we hit a. The second case means that something before n makes g of n hit a, because a would have the smallest f value for something that is before gn. Okay. So G is surjective. Okay, so we have a bijection. Well, having that bijection means that we've proved our theorem. We've proved that A is countably infinite. So let's go back to the book. Okay. Not every subset of n is countably infinite. Yeah, so if you don't pick an infinite subset, you're not going to end up with a countably infinite subset. This set, this number here, or this symbol here, this is called Aleph naught. It just means the cardinality of the natural numbers. Okay. Example, are the even numbers of the same cardinality as the naturals? Yes, and we actually have, oh, well, they give us a function here, but we have a proof that there are as many evens as there are naturals. It's not that hard of a stretch to go from there to there are as many evens as there are integers, since if there is the same number of evens as naturals and the same number of naturals as integers, then because we proved that cardinality is equivalence relation, we get that there are the same number of evens as there are integers. Okay, so let's look at these exercises. Let's see. Declare whether the following statements are true or false with a proof or a reason. Sorry, with a proof or a counterexample. Okay, all finite sets have the same cardinality. That's false. The set that has one element has a different cardinality than the set with two elements. Okay. If f goes from a to b as a function between two sets, then the order of f is the order of a. Thinking of f as a set of ordered pairs. Yes, that's true. And it's not so bad of a proof. If f is a set of ordered pairs, then these ordered pairs have two coordinates. The first one is the element of a. If you have a function, then you have two properties. You know that f has a value for every element of a, and you know that f does not have two values for every element of a. So the cardinality is at least a, because f has a value for every a, so it's at least the cardinality of a, and it's at most the cardinality of a because f has at most one value. So the bijection here is going to be something that looks kind of like this. So we define G goes from F to A by G of A F of A equals A. So we're taking an element of the function and spitting out an element of A. Well, is this injective? So we have, suppose G of X equals G of Y. Then that means that A sub X comma F sub A sub X, G of this equals G of, we have A sub Y comma F of A sub Y. There we go. So that means what? Well, that means that A sub X equals A sub Y. So a sub x comma f of a sub x equals a sub y comma f of a sub y, and that's our proof. That's injective. What's surjective? Well, suppose let's say y exists in A, because that's the codomain. Then y comma f of y. Well, that's obviously in F, right? And g of y comma f of y equals y. Hey, that's what we're looking for. So it's surjective. So if we're injective and surjective, we're bijective. That's the bijection we need. Okay, so let us look back at our book. We say every subset of the natural numbers is countably infinite. This was explicitly in what we just read. Like, hey, look, subset of n that's not countably infinite. You can just pull that example straight into your homework. Okay. So, every subset of an infinite set has cardinality L if not. Ooh. Well, that's false. Because, for example, okay, so every set is a subset of itself, right? So if we have a set that has, an infinite set that has a different cardinality, it's a subset of itself that doesn't have this cardinality. And it's an infinite set because if set A is an infinite set without cardinality L if not, then A is a subset of itself that happens to still be an infinite set and still not be cardinality L if not. So we just have to know, is there a set that's infinite without cardinality L if not? Well, let's see. For that, we'd want to go back and look up the definition of L if not. I told you what it was, but we want to be thorough, you know? I'm modeling this live stream based off of how I would study this if I were in this class. So we'd go back, hey, look, here's a cardinality. It gives no examples of different cardinalities. Let's see. Are there any sets which are infinite but not countably infinite? These would be sets which occur strictly above this in the diagram. We will prove in section 30 that yes, there are such sets. Okay. So, if they don't give a proof that there is such a thing as an LF1 set, for example, in this section, but assert that it exists, we will do the same thing. We will say, in section 30, there is an LF1 set. It is infinite, has a different cardinality than L if not, and is a subset of itself. And that'll be our proof of D. Now let's look at E. If f goes from A to B as a surjective function, then the cardinality of f is the cardinality of B. Well, that's not true, because I can get a surjective function from, let's say, the set containing 1 and 2 to the set containing 1. Okay? So let's write this out. Switching over to our... Here we go. So let's say we have f goes from the set containing 1 and 2 to the set containing 1 by f of 1 equals f of 2 equals 1. So this set just takes every element, which there are only 2 of them, but there are these 2 elements, and sends them to 1. 1 goes to 1, 2 goes to 1. Okay? This is surjective. But the cardinality of the set containing 2 elements is 2, and the cardinality of the set containing 1 element is 1, and 2 is famously not 1. So this is our contradiction, or our counterexample to the statement. Let's look back at our book. Okay, so define h from the interval from 0 to infinity to the interval from 0 to 1 by this. Verify h is a bijection. What does that say about the cardinality of open intervals? It says that it's the same cardinality. That's what this means. If we have a bijection, we have the same cardinality. So we're going to prove that we have a bijection. Okay, so our bijection, we claim f of x equals x over x plus 1 is a bijection from 0 to infinity to 0 to 1. So let's prove injectivity. We want, suppose f of x equals f of y, then x over x plus 1 equals y over y plus 1. So xy plus x equals x. We're just cross multiplying x, y, x plus 1 gives us xy plus x. And then we have xy plus y. We'll subtract off the xy from both sides. That's a terrible color to cancel things in. Cancel those. And what are we left with? Well, we're left with x equals y. That is not y equals y. X equals y. That proves injective. Now we want surjective. Well, surjective is, suppose y exists in 0 to 1, then what? How do we get, well, we're going to need to do some scratch work, because usually we have to for surjectivity. So this is how we would do this. Say y equals x over x plus 1. Well, how do we figure out what x to plug in to get y? Well, we're going to have to do, we're going to have to invert this function. So we're going to solve for x. So we get xy plus y equals x. That gives us xy minus x equals y, negative y. This y goes to the other side. This y goes over here. This x comes over here. We get the negatives there. Okay, so that gives me x times, gives me x times y minus 1 equals negative y. I'm going to cancel on both sides, like so. We get x equals negative y over y minus 1. So now that we've done our scratch work, we go back over to our proof. So we say, let x equal negative y over y minus 1. Then f of x equals, well, it's going to equal x over x plus 1, which equals negative y over y minus 1 over negative y over y minus 1 plus 1. Well, what does that equal? We're going to multiply everything by y minus 1 over itself so that we can get rid of the compound fraction. Multiplying by something over itself doesn't change the value of the fraction. So we get negative y on top, and we get negative y plus y minus 1 on the bottom. Well, the negative y's will cancel. the negative y will cancel with the positive y, is what I mean to say. And then we get a negative y on top and a negative 1 on the bottom. The negative signs cancel, leaving us with just a y. And that's what we wanted. We wanted to find an x such that when we plugged in x, we got out y. And that was the one that we needed. So here's our proof. We do have a bijection. Okay, so if we have a bijection, as the book asked, this shows that we have the same cardinality. So prove that there are that the set of natural numbers with exactly one of the digits equal to 7 is countably infinite. Okay, so this is a subset of natural numbers. There's a theorem that we passed. It is here. Any infinite subset of a countably infinite set is countably infinite. We're trying to prove that the set of natural numbers with exactly one of the digits equal to 7 is countably infinite. So, since this is a subset of a countably infinite set, if we can prove it's infinite, we prove it's countably infinite by the theorem. What was that theorem again? 2813. Okay, let's go back to our canvas. There we go. So, theorem 2813. If A is an infinite subset of a countably... Oh, this would have been useful in the long theorem that we proved earlier. No. I'm sure that the long theorem we proved was used in proving this theorem. If A is an infinite subset of a countably infinite... Oh no, this was the theorem we proved. Yes. If A is an infinite subset of a countably infinite set, then A is countably infinite. There we go. This is the theorem we're going to use. This is the homework problem. So we want to prove that the set of natural numbers with exactly 1/7 in its decimal representation is countably infinite. So this is the problem we're trying to prove. This is the tool we're going to use. Proof. Since the set of interest is the subset of natural numbers, or is a subset of the natural numbers. Theorem 2813 implies that proving this set is infinite is sufficient. To prove that it is countably infinite. Okay, so that's the first step. That reduces the work a lot because all we have to do is show that there are an infinite number of numbers that have exactly 1/7 in their representation. So for any n in the naturals, let f of n equal a 7 followed by n zeros. I guess the way to write this would be equals 7 times 10 to the n. So, what does that tell us? Like, tells us there are infinitely many numbers that are 7 times the power of 10. These all have exactly 1/7. As a digit. So, the set of interest is infinite. And thus countably infinite. Okay, so did I miss any numbers that had exactly 1/7 as a digit? Absolutely. Does it matter? No, not at all. I proved that there are an infinite number of numbers of the form 7, 0, 0, 0, dot, 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 0, 0, dot, dot, dot. I proved there are an infinite number of those. So obviously there are an infinite number of any number that has a exactly 1/7 in it. And then by the theorem that we looked up, that proves that there's a countably many number of them. There are countably many of them. And that's a really nice, simple way of doing this proof. So, well, we are over time now. But if you have any other questions about cardinalities or functions or anything from the book, or you aren't one of my students, if you have any questions about math at all, send me an email and I'll get back to you. So, have a great day. Talk to you Thursday.